Neurips 2025 paper discussion, DataRater. This is a paper by a bunch of people, amongst which is David Silver. I think he's one of the people I pay attention to because he was basically the creator of AlphaGo Zero, which in my opinion is one of the biggest breakthroughs in AI, still up to date. For people who are not familiar, just please go check it out, what AlphaGo Zero did. It created a self-play engine that was able to learn how to play Go and later on other games. So really interesting. So what this paper does, and it was part of Neurips 2025, it's solving a problem that is very prevalent in AI, and that is which data should we actually use for training. Now that has two massive implications. One is of course cost, but the other is also if you have better data, you also get better models. Garbage in, garbage out. Now there's maybe a school of thought, sort of along the lines of the bit of lesson, which is, oh, look, it doesn't. If you had unlimited compute and unlimited amount of money, you just train on everything and then let the model figure it out. But that's not the world we live in, right? We do have constraints, and those are, we have real constraints. And even though we want to keep our models as general as possible, and the data as general as possible, and the variety as general as possible, and all of that stuff, I think there's still value in selection. And what this paper is attempting to do is automate selection. So solve the which data should I use for training question as an optimization problem. What they use is what they call meta gradients, which is, the idea is the following. In a typical model, like a normal large language model or convolutional neural net or gradient net or whatever, what you're doing is you're using gradient descent, so you're looking at how the next available input data is reducing the error rate that you're training against. In meta gradients, you're looking at how the next possible data point is improving the learning rate. So you're not looking at how the model actually performs, but how the rate of performance changes. So it's sort of a second derivative. So I think that's the fundamental idea here. I think the biggest question that I have is, where is the cutoff, right? The problem with data is, like the intelligence is the computational part of learning how to adapt to reality. That's what intelligence is. And we can do really, really well with, maybe 80, 90% of problems in the world. We can adapt really well, whether it's self-driving cars, robots, large language models. We can do really well, but we have issues with the edge cases, and they're always prevalent. And in fact, some people might say the edge cases are really where we learn. So edge cases being, the situation where the Tesla drives into a parking lot and there's a sign which says physicians only parking. That's an edge case. It doesn't happen very often, but it does happen sometimes. Is this now a data point that is useful or not? I would say it's very useful. But maybe the real data point that's useful is not this particular sign, but the fact that when you're driving into the parking lot, it said hospital. And you might say, well, that's not very useful. I mean, who cares whether I'm driving into a hospital or a school? It's a parking lot. Well, it actually matters, because when I'm driving to a hospital, you might want to pay attention to a sign which says physicians parking only, and when I'm driving to a school, you might pay attention to a sign which says teachers parking only. So how do we know which data is when important? And the question here is, at what point do we cut off data, right? Like I asked myself, for example, the question of snow, right? Is snow important when you train a self-driving car model in Southern California? It is probably irrelevant because you never have snow, but then sometimes you do, and then that's really key. So how do you know? Now, the authors do talk about this, and they talk about, for example, not eliminating any data, but reducing the weight of the data, which is kind of like asking, well, then you're really not saving a lot of money on the data side of things, but at least you're saving money and time on the trajectory type of thing. So you're not crunching all the data all the time. So there's these are open questions. I think the paper is interesting for opening up this debate and also offering some solutions. I think in general what we want is, of course, self-supervised, optimizable engine that selects the right data for training. That would be very useful, at least for now. Maybe going forward we can solve the problem in compute and of course memory. Memory is the big bottleneck here. It's not even compute. So we can't train on all the data. I mean, it's kind of like a human, right? I mean, you go to Berkeley. You're 18 years old, and you can ask yourself, well, how about I study everything, right? Well, who cares? Like, why should I even commit to a major? Well, you want to commit to a major because it's just not very efficient to study everything. You're not going to be very good at things, and you might want to focus. So what do you focus on? Well, how about you look at what is the incremental usefulness of a certain class relative to what? Well, relative to a goal, of course, which is maybe I want to get rich, or maybe I want to win a Nobel Prize, or I want to impress my family, or whatever your goals are. So I think we're opening up a lot of questions here about what's the goal, what's the purpose of an AI, what does it even mean to be intelligent. But I think in general, again, the paper itself, very useful just to open up these questions, offer some solutions. I think we can iterate around these solutions. I think we can get better. But for now, this is, in my opinion, a very interesting contribution. Thank you.